Hi, everybody. Today we are going to talk about limits and continuous. So in this video, we are going to explain the continuation of limits, and we are going to understand the continuity as an important part of calculus. So before we understand the continuity, let's remember what was the idea of limits here. So we said that the limit of at any point of the function x limit x approaches to c, and at any point c fx is a kind of the number where fx approaches to. So when if we draw the graph here, let's draw some graph and try to remember what we had in our previous video. So we said that regardless of the point C included in the domain, so it can be included or it can be empty point here. So regardless this point is included in the domain, then when we take x from left side and right side, when we approach to C, our function approach to some certain number here, which we call the limit of the function. So the idea of the limit also is used with the idea of continuity. And today we are going to talk mainly about the continuous functions and which cases gives us the discontinuities. So which cases gives us the continuities and which cases that do not give us the continuity, which we call discontinuity. So let's take a function fx. Yeah, it has got some domain x. So it's important to differentiate between c x equals to c that we talk here with x equals to c that has been talked about in the limit section. So if you remember in the limit section, we said that x should not be in the domain. However, here we are going to include x equals to c. We are going to include in domain. So it's one of the important things that the function should be defined in domain x at point c. So let's suppose we take such a c from x. So graphically, what does it mean graphically, the continuous function? Graphically, it means that if the graph of a function, if we can draw the graph of a function without taking the marker from the board, then obviously this function is a continuous function. If I draw the graph by taking the marker here outside, so you in this case we get the interruption here or discontinuity here in mathematical language. So let's try to understand the definition here. By definition, it's let f be a function defined at least on an open interval c minus bc plus b. We say that f is continuous at point c if the limit value is corresponding to the function value at c. So what does it mean? It means that the limits that we used to find in the previous section at c, it should exist. And also, there is one more condition that it should be equal to fc. So there is no way out running away from fc. And we have to, this time we have to take care of fc, and they should be equal actually. Fc should exist and it should be equal. So now let's see an example. For example, function fx equals x squared plus 3x. If we take such a function, it's obvious that at any point, if we take any point, for example, 0.5, any point from the domain, then the limit value of this function is going to be limit x tends to 5, x squared plus 3x. Obviously, it is going to be 25 plus 15, 40. But we shouldn't forget that f5 is also 40. So they are equal. So we can say that the function is continuous at point x equals to 5. But anyway, this function is continuous everywhere at any point of the domain. We are going to talk about it a little bit later. So our today's purpose is to focus on continuous at the point. Uh, However, if we have such a function, for example, if x equals to 1 out of x minus 2, obviously x equals to 2 is not does not belong to a domain. Moreover, at this point, the limit doesn't exist, so we get the continuity infinity here. So in this case, we see that this equality here violates. So the definition violates. It means that the function, this function is discontinuous at x equals to 2. But for other points, for example, if we take x equals to 3, then limit x tends to 3, you can see 1 out of x minus 2 is going to be equal to 1. And f3 is going to be also 1. So they are equal. So at any other point rather than 2, we have got here the continuity. The function can be discontinuous at 1 point and at 2 point, and it can be continuous at many other points, infinity many other points. So from these examples, we see that the domain of the function plays an important role here. So let's go in detail on continuity and moreover the discontinuity case. So let's look at this equation. So in this equality, limit x tends to c, if x equals to fc, we said that this is the mandatory condition, compulsory condition for having c the point of continuity. And now let's consider when in these cases, in which cases can this equality violate? So can this equality this equality is not true? So the first case, it might be possible that limits x tends to c exists. So function limit at c exists, but it's not equal to function value. There might be several reasons for that. Function value fc might not exist, or it might exist, but it's not equal to limit value. So anyway, this says us that the function is not continuous at c, it's discontinuous at c. Such a discontinuity we are going to call a removable discontinuity. So I will show on the picture, on the figure, why is it removable discontinuity, why we call it removable discontinuity. Look here on this picture, you can see function is defined as c, so there is no problem with the domain. We have a value of c, but the limit value here, you can see the limit value here is L. So the function has the limit at c equals to L. But the function value at c, fc is different than L. So you can see fc is different than L, the limit value. So it tells us that the function is discontinuous at point c. It's not continuous at c. And what type of discontinuity is this? As we mentioned, it's a removable discontinuity. But how we can be sure that it's removable? Why is it called removable? Because if we could take this point from here and transform here, then you're going to see that there is going to be 100% match for the curve. And in this case, FC will correspond or equal to L. So seemingly in this way, if we could do this, here the violation of the violation of the continuity will be eliminated. So it would be removed. It doesn't mean that we can do it right now, but if we say if we could do it, it could be removed. So in this case, we say that it's a removable discontinuity. Let's continue to analyzing our equality of, we said that this equality provides the continuity of the function. And the second thing is that uh, limit might not exist. Even at the point limit fx doesn't exist. There can be different reasons. Let's count when limit cannot exist. First of all, there can be left side limit and right side limit. They might exist, but they might not be equal. So we know that if the limit exists, then the right and left limits should be existing and they should be equal, and vice versa. So if limit doesn't exist, so more obviously, one of the limits might not exist. So this is another case. For example, one of the limits might be infinity, or both of them might be infinity or might not exist. In this case, the limit doesn't exist. So this case gives us a discontinuity, which is called an essential discontinuity. I will focus on this discontinuity now. So an essential discontinuity also has two types. Let's see the next figure here. So you can see here, first of all, let's look at figure 2.4.2. You can see here at point C, there is an interruption here. This is because the limit doesn't exist. So we have here another value here for right limit, and this is the value for left limit. You see they don't coincide, so it says as the limit doesn't exist at the point. So at point C, there is a violation of limit existence. So limit doesn't exist. It means that definitely the function is discontinuous at that point. This such a discontinuity is an essential discontinuity, but however, it's a special type of essential discontinuity which we call jump discontinuity. Also, we can have other essential discontinuities. For example, look here at point C. By the way, here the function is defined at C. At point C, we have left limit plus infinity, right limit negative infinity. So the limit doesn't exist, obviously. So it's an essential discontinuity. So such a discontinuity we call infinite discontinuity. So infinite discontinuity is also essential type of essential discontinuity. So here you can see in the second figure, you can see left limit is this certain number, right limit is infinity. The limit obviously doesn't exist. The same case for the third figure, left limit is negative infinity, right limit is the certain number. Obviously limit doesn't exist. So in all these cases, we are talking about the infinite discontinuity. So infinite discontinuities might arise not only from, we can see it not only from pictures, but we can also consider some examples. And today, as an example, I'm going to consider such a function in order to understand. But before I do it, let me take another one, the easier one for the start. So let's call it example one. Example one. Okay, fx equals to, let's suppose we have got such a piecewise defined function, 2x minus 1 if x greater than 3, and fx equals to 5 if x let's say that is less than or equal to 3. So let's see the function set up here. So limit x, first of all, let's write limit x tends to 3. From left side, let's see fx is equal. If we consider this limit from left side, so left side of 3, we are going to have this part, which makes us 5 here. Now let's consider limit x tends to 3 from right side. And in this case, fx, we are going to have this case. So if you put here 3, 2 times 3 is 6 minus 1 is 5 again. So you see they are equal. So obviously we have got here the equality of limits. and then limit x tends to 3 exists. So we can write it's equal to 5. And at the same time, f3 is equal. If you want to calculate f3, we are going to look here because x less than 3 is included here, so it's going to be 5. So we see that they are equal. So x equals to 3 is the point of continuity here. But however, if we change here this 5 by another number, for example, if I change it, let's say for 7, let's see what happens in this case. In this case, limit x tends to 3 from left side of x is going to be 7, as I said before. And limit x tends to 3 from right side of x is going to be 6 minus 1, 5. So you can see that they differ. It means that the limit doesn't exist. If limit doesn't exist, we have left limit, right limit. They exist, but they are not equal. It means that this is a discontinuity, which we call jump discontinuity. Now let's continue another a little bit harder case. So I'm going to put it here, our function. So I'm going to analyze for each point here. So which points we have here on the boundary? We have got here x equals to -1, x equals to 1. Another boundary is x equals to 4, x equals to 7. So 4 points. We are going to consider 4 points. First of all, let's start from x equals to -1. For this case, let's consider the limit value. So x tends to -1 from left side, fx is equal. Negative part less than -1 is this case. So it's going to be -1 cube. And if we can see that limit x tends to -1 to from right side fx, it's going to be, let's see, it is right side of fx is closer, is this part. So it's going to be here. We are going to calculate here. Again, -1 square minus 2 is going to be -1. So we see that they are well equal. And now we have to find f-1. So f-1 is going to be, we need to calculate it here, f-1. So it equals to -1. Okay, so for this point, we got that it's continuous here. We found that the function is continuous because the limit values are coinciding with the function values here. Now let's consider the second number here. The second number here is x equals to 1, the second point. So x equals to 1, we need to first consider the limit values from left side of x. You can see left side of 1 is going to be calculated here. 1 squared minus 2 is equal -1. Limit x tends to 1 from right side. So right side of 1 takes into consideration this part. So it's going to be fx is going to be 6 minus 1, which is 5. So you can see that they differ. If these values are different, then the limit doesn't exist. So in this case, we have the discontinuity. So continuity is violated. So we have discontinuity. And in special case, we have jump, essential and jump discontinuity. Now let's consider the other one. We have 2 more points here. Yeah. So we have x equals to 4. Looking in the function, we can obviously see that at x equals to 4, we don't have f4. So f4 is not defined here. It means that we are going to have the violation of this. So obviously it is discontinuous. So we can write here, discontinuous. So in order to define the type of discontinuity, we can find the left limits. Limit x tends to 4 from left side of x. From left side, we are going to have 6 minus 4, which is 2. And from right side, we are going to have this one. So it's going to be 6 out of 7 minus 4. So 6 out of 3, which is 2. So you can see they are equal. It means that our discontinuity, you see the limits equal, but it's not equal to F4 because F4 doesn't exist. So it's kind of a removable discontinuity. So obviously, if it existed here at F4, or if we could, if we had the authority to do F4 equals to 2, then they will be both equal to this. Then the discontinuity would be removed. That's why we call it removable discontinuity. And now consider the last one. Let's consider the last one. X equals to 7. So at point x equals to 7. Limit x tends to 7 from left side, fx, is going to be, you can see here, from left side, 6 out of 7 minus 7. So it's going to be infinity. And also the from right side, we are going to get x tends to 7 from right side. We will take, of course, the last equation. Fx is equal to 5 times 7 plus 2, 37. So you can see they are not equal. Limit doesn't exist. And obviously, we have here discontinuity. We have here discontinuity, and this discontinuity is kind of infinite discontinuity. Infinite discontinuity. So at 2 points, we have, at these points, we have essential discontinuity. And in the first case, we have jump, and in the last case, we have infinite discontinuity. For point x equals to 4, we have again discontinuity, which is removable discontinuity. And for x equals to -1, we have continuity. The function is continuous at -1 because limit values are associated with, they are equal to the function value. So that was all for today. I hope you enjoyed the video. We are going to discuss this idea in our next videos also, so do not hesitate to contact with me or to write in the comment section your ideas about this, and also which topics you would like to see here, which explanations you would like to see. I'll be glad to help. Good luck to you. Have a good day. Bye. Take care.